All right, we are given that cosine of 2 alpha equals 3 over 5. That cosine of 2 alpha should tell us that we should go to our double identity sheet, which is not there, apparently. It's there. And it tells us to find the one that has cosine of 2x in it. The thing is, we do have 3 of them. We have that guy, and that guy. Only 2 of them will help us, 1 will not. Since I know the value of cosine 2x, we know it's 3 over 5. If I make this 3 over 5, I can't solve for cosine, nor can I solve for sine, because I can't get it by itself. However, if I replace this cosine of 2x with 3 over 5, I can then add 1, divide by 2, and then take the square root, and I can actually solve for that given value. So let's go back to this. So I'm going to use that fact that I can rewrite cosine of 2 alpha. Using my identities, I can write this as 2 cosine squared alpha minus 1. Or you could have actually done the one with sine in it, and you would come up with the exact same answer. All right, so I picked that one. You are now going to take that 3 over 5 and replace it for that entire quantity. Once again, I don't want to see this on the test. I don't want to see you just replacing it in there and then you're looking for cosine of 3 over 5, which doesn't work. You're going to replace the entire thing with 3 over 5. So then we have 3 over 5 equals 2 cosine squared alpha minus 1. Add 1 to both sides. Adding 1 to both sides is actually adding 5 over 5. So that's going to be 8 over 5 equals 2 cosine squared alpha. When I divide both sides by 2, sometimes just to make it easier with fractions, I think about it as multiplying by 1/2. Sometimes it's easier to see. If I multiply both sides by 1/2, I'm going to come up with 8 over 10 equals cosine squared alpha. I'm going to, first of all, I'm going to reduce this. This is actually 4 over 5. Can we all see that? It's just 4 over 5. And then I'm going to take the square root of both sides. So that's going to give me cosine alpha equals the square root of 4 over the square root of 5. Now it's either plus or minus, because when you take the square root of both sides, it's either plus or minus. If we look here, our double angles in quadrant 1, which pretty much automatically means that our other one has to be in quadrant 1, because the biggest angle I could have would be 90. And if I took half of 90, it'd be 45. But just for the sake of doing this lesson, to figure out where alpha would be, you would divide everything by 2. So that'd be 0 divided by 2, which is 0 degrees, is less than 2 alpha divided by 2, which is alpha. 90 divided by 2 is 45 degrees. So everything's in quadrant 1. So that must be a positive square root of 4 over 5. Well, square root of 4 is actually 2 over square root of 5. Quick shortcut. Does the problem ask you for cosine? No, you don't need to simplify it. You can leave it as 2 over square root of 5. You could leave it as square root of 8 over 10. I don't care. We're just going to use it to get to tangent, because tangent is sine over cosine. So I need to get cosine first, and then I'm going to go ahead and I'm going to get sine. So once you know cosine, you can easily get sine. So to get to sine, we're going to say, well, sine alpha equals plus or minus the square root of 1 minus cosine squared alpha. Well, first of all, we're in quadrant 1, so it must be positive. It's the square root of 1 minus 2 over square root of 5 squared, which is going to equal, I'm going to change the 1 to 5 over 5. Minus 2 squared is 4. Square root of 5 squared is 5. So sine alpha is going to equal a positive square root of 5 minus 4 is 1 over 5, which is really 1 over square root of 5. And finally, we have to get our tangent value. Don't forget that tangent of alpha does equal sine over cosine. And our sine value in this case is 1 over square root of 5. Our cosine value is 2 over square root of 5. So this whole thing's going to equal 1 over 2. If you struggled on this one, just realize that this was pulled straight from the homework. The only thing I changed was, I think the homework was cotangent. So make sure when you're going through these, if you're struggling with something, go through your notes, go through your homework. More than likely, I pulled it out of one of those things. I want to do this another way. I think I did in this class too. I'm going to do it again. We don't have to do any of this if you don't want to. You did have to get your cosine. But we can go a completely different way with it if you want to. So just remember that cosine. We got down to the fact that cosine alpha equals 2 over square root of 5. And don't forget that cosine, sine, and tangent are all dealing with a right triangle. So you could still use right triangles. You could say, okay, I have a right triangle. I'm going to call this my alpha. Cosine is ca, which is adjacent, over hypotenuse. So this is just a right triangle that has a base of 2 and a hypotenuse of square root of 5. Then you could just say this is side A. And you could say a squared plus 2 squared equals square root of 5 squared. And if you solve that out, you're going to come up with a equals 1. Which means if I'm looking for the tangent, tangent is TOA. It's opposite over adjacent, which would just be 1 over 2. Your tangent would be 1 over 2. So if you didn't want to, you didn't have to do either of these last two columns. You could have just did a right triangle as well. We didn't do much of that because I wanted you to know these because they're really great for doing the identities. But now if you want to use right triangle, use right triangle. All right, questions from the homework. What did we do? 6.6. Leo. 11. Art 11 says cotangent of theta equals 4 over 3. And theta is in quadrant 3. We're supposed to find sine of 2 alpha. So what you're going to do is we need to find sine of 2 alpha, so you need to go to your double angle formulas. And sine of 2 alpha is right here. In order for me to get to sine of 2 alpha, I need to find the value of sine and cosine. So that's really all they're asking for is find sine and cosine, plug it into that formula, and you have sine of 2 theta. Well, we started off with cotangent is the problem. Anytime we start with cotangent, tangent, or something square and we need to convert it to sine or cosine, you're always going to look at your Pythagorean identities. And your Pythagorean identity, if you look at one of them, it says 1 plus cotangent squared theta equals cosecant squared theta. Well, cosecant is basically just sine, the reciprocal of sine, so it's in sine and hiding. So you are going to take that identity. You are going to take that identity, you are going to write it out. And you're going to fill in the blanks that you know. So we were given cotangent. So if I look at my identity to get to cosecant, I have 1 plus cotangent squared equals cosecant squared. Well, I'm going to take that 4 over 3 and plug it in for that cotangent. Which, working all the way down, I solve for cosecant. Well, that means sine is just a reciprocal, so now I have sine equals negative 3 over 5. In every one of these problems, once you have sine or cosine, you're pretty much done with the problem. Because whether you use a triangle or whether you use this formula, you should know how to go from sine and get cosine. So if I know sine is negative 3 over 5, I can say cosine theta equals the square root of 1 minus sine squared theta. plug in that negative 3 over 5, solve it, you get your cosine theta equals a negative 4 over 5 because we are in quadrant 3. Then we just plug those values in to our formula. Negative 3 over 5 for sine alpha, negative 4 over 5 for cosine alpha, and you have your answer. So the really hard step you had to do was remember your Pythagorean identity, which cotangent can be converted to cosecant. All right, other questions? Grace. 17. Oh, real quick, before I say anything, 15 and 16 were supposed to be different problems. They were the exact same problem. Doing 15 and 16 is the exact same problem. It was supposed to be different, but I didn't change it. Did you recognize that? Okay. It was supposed to be different. If you look at my answer key, I actually solved it for a different one. But they were the exact same on yours, so unfortunately. But we are on 17. So I guess that's neither here nor thither. All right. So we were given tangent squared theta equals 1 minus cosine 2 theta over 1 plus cosine 2 theta. So once again, whenever you're doing problems like this, you should immediately see this cosine 2 theta and say, I need to change that. I need to somehow get it to just thetas. So you're going to look at your double angle identities. Let's get mine up here. But once again, we come across that problem that there's 3 possible ones to pick from. So I don't know for sure which one I need to pick. So rather than just guess and checking your way through it, because you have 3 possible on top, 3 possible on bottom, so you have a whole bunch of different combinations. Instead, we're going to look at the left-hand side and say, well, tangent isn't written in terms of cosine like I'd like it, so I can see what we're doing. So my first step would be either to think about what tangent is or to actually write that tangent is just sine squared theta over cosine squared theta, because now it's in terms of at least cosine. And what I'm going to do is I'm going to recognize that sine squared is in the numerator. Cosine squared is in the denominator. So as best as I can, I want to pick something that just has sine in it in the numerator, and I want to pick something that just has cosine in the denominator. So if we go back to our 3 possibilities, if we look at this third one, that's going to work great for our numerator because it just has sine in it. If we look at the one right above it, that would work great in our denominator because it just has cosine. So that is what we're going to choose to do. We're going to rewrite the top one using that sign. So we're going to have 1 minus, and our sine one is 1 minus 2 sine squared theta. On the bottom, I'm going to replace that cosine 2 theta with that 2 cosine squared theta minus 1. And if we look really quick, we're going to have 1 minus 1, which is going to turn to 0. We're going to have this negative go here, so that's 1 minus 1, which is 0. This negative is going to go here. We're going to have a positive 2 sine squared theta over 2 cosine squared theta. 2's cancel out, and I am done. Once again, this just boils down to noticing that cosine 2 alpha and rewriting it. Looking at your double angle identities and rewriting it. All right, other questions? Yeah. Number 14. 14. 14. We start off with sine 2 beta. So in fact, before I do anything else, I'm going to rewrite that using the double angle formula. So I'm going to rewrite that side without even thinking. I'm going to write it as 2 sine beta cosine beta. All right, we're done with that side. That's as far as we can go on that side. Our other side is negative 2 sine beta times sine beta minus pi over 2. I'm going to highlight that little section right there. This is the only thing I can actually work with. Sine b, the only thing I could do is potentially, I don't even know what I would do with that. There's not much you can do with sine b unless it's squared. So what we are going to do is we're going to recognize, either you can recognize this as a cofunction, you don't have to at all. But what I'm going to recognize is this is a subtraction of angles. This is a subtraction of angles. So we're going to leave that negative 2 sine b on the outside. And we're going to treat that as alpha minus beta. Well, if you have sine of alpha minus beta, you can rewrite it as sine of your alpha, which is beta this time, so that's kind of confusing, your first angle, times cosine of your second angle, minus cosine of your first angle, times sine of your second angle. And here's where it becomes really important that you know how to read your unit circle and know values. Cosine of pi over 2 is 0. If you look at your unit circle, that is 0. Sine of pi over 2 is 1. So this whole thing is going to cancel out. And this is just going to be cosine b. So you're going to have a negative times a negative. So this side is just going to be 2 sine b times cosine b. But that's what we had on that side. Other questions? Leo.
15 and 16.
Same problem. Yeah. We do not have a triple angle formula. So this is kind of a knee-jerk reaction. We've been doing this since the last test. If you don't have what you like here, turn it into addition. Turning it into cosine 2t plus t. Then I can use my angle addition property, say, well, it's cosine 2t cosine t minus sine 2t sine t. I can rewrite my sine of 2t as 2 sine t cosine t. The only part that really you have to think about is this cosine 2t. You have 3 possible ways to rewrite it. That is either sine squared cosine squared. You can write it as that 2 cosine squared minus 1, or you can write it as 1 minus 2 sine squared t. A good sign that you're not going to use the ones with 2's in it is there's no 2's over here. You'll see something like, it'll say something like 2 cosine t over here or something. So more often than not, if you just have a cosine cubed, some sine squareds, you're almost always going to turn this into cosine squared t minus sine squared t. And then it's just distributing and simplifying, and you'll have the other side. All right, other questions? The one I was supposed to do down below would be where you'd use like 2 cosine t or something, because you'll see that my original plan was to have you do 2 cosine squared t, 2 sine squared t, then you'd have to use a different one. But those 2's would stand out as I have to use 2 something. All right, other questions? All right, just to be clear, test next Friday. Test next Friday. And these will be on there, I guarantee it. All right, moving on to today's lesson. Today's lesson should be kind of a step back as long as you know how to read a unit circle. If you don't know how to read a unit circle, then you're going to struggle, and you probably already have struggled. But today we're going to talk about solving trig functions. We've already done these. The only big difference between what we have done and what we're going to do today is this word right here. All. Find all real numbers that satisfy each equation. That all tells you need to find every possible angle, including all coterminal angles. So I put it as, for all solutions, we must find all coterminal angles. So we must find all coterminal angles. So the problem with that is there's an infinite number of coterminal angles. You can always add 360 over and over and over, and you can always subtract 360 over and over and over. So we'll tackle that in just a second. The first thing we're going to look at is cosine x equals square root of 2 over 2. All right, another way to think about that, so I could rewrite that, is this is really cosine inverse of square root of 2 over 2 equals x. In other words, you go to your unit circle, you find where cosine equals square root of 2 over 2. Remember, inverse will always get you an angle out, so this will always result in an angle. Where is cosine equal to square root of 2 over 2? Positive square root of 2 over 2. Yeah. 45 degrees, that's one of them. Where is the other one? Because we know cosine's positive in two different places. Yeah.
115 degrees, right?
Sure. Oh, it makes sense too, because this is a positive 45. That really is just a negative 45, right? 360 minus 45. Those are the two places where cosine equals square root of 2 over 2. However, I said that we have to list all of the possible coterminal, and rather than writing them all out for infinity, instead we're going to rewrite this as, well, that's where x equals 45 degrees plus any number of adding 360s or subtracting 360s, because k could be a negative 1, which would be 450 or 45 minus 360. Then if I have to list all the solutions for 315, I'm going to say, well, wherever x equals 315, or if I add 360 to it however many times I want to. Now we're going to write both of those in, Isabel, can you pull up? Thanks. We're going to put all those into one function, and this is going to be called set builder notation. Set builder notation opens with a brace, and it says for any x, and then you put a vertical line. That vertical line just stands for such that. So what we have right now is x such that x equals 45 plus 360k, or, and this should all be in the same thing, I'm just running out of space. Maybe I'll just slide this over real quick. And then let's erase some of those arrows just so I can fit it all in one line like it's supposed to be. Or x equals 315 plus 360k. Close brace. So this is a list of all real numbers that work for that x. As long as it fits this scenario, it will be square root of 2 over 2. That's all we're doing today. And it's basically what we're doing today. If you can read a unit circle, today is going to be really easy. So the next one is sine of x equals negative 1/2. Once again, if you know your unit circle, this is going to be super easy. Or if you don't know your unit circle, it's going to be really hard on the test. Your choice. Either you've been practicing your unit circle or you have not. Where is sine of x equal to negative 1/2? Knowing that sine must be negative down here, and it must be negative down here. Yeah.
210?
210?
Yes.
And where else? 330, yes. Perfect. So we could say, with step builder notation, that's going to be x such that x equals 210 degrees plus 360 times k, or 330, yeah, I should have x equals. No shortcuts. X equals 330 plus 360 degrees times k. That's it. That's the whole problem. All right, where does cosine x equal -1? Use radians. Where does cosine equal -1? Use radians. And we have Chris. 315? I don't think it's 315.
Oh, cosine of that cosine. Sorry.
Okay, yeah. 270? Maybe. I don't know. Grayson? Pi? Probably pi. Because this is the point -1, 0. Right? It's -1, 0. So our cosine must be -1 there. Well, we have no other place where it's -1. It is just in that one place. So since it's just occurring in one place, we just have to write one short statement. That is x such that x equals pi plus, what's 360 in terms of radians? Someone. 2 pi. So we'll have 2 pi times k. All right, where does sine x equal square root of 3/2 radians or degrees? I don't care. Yeah.
I think we have to use radians on the last one. But
Oh.
did you just say that just to show us that we can?
Mm-hmm.
Oh, okay.
Because you're going to have to look at the directions to see what you have to write. And if I do this entire lesson in degrees and I put radians on the homework, you'd be like, well, we didn't do those. Yeah. So on the homework will tell you, the test will tell you. All right, I'll say specifically in radians, or I'll put degrees, or I'll put, you choose. All right, where is sine of x equal to square root of 3/2? Use radians or degrees. I don't care. First person pick that answers. If you don't know unicircle, you should have a unicircle out, so you should be looking at this stuff. Yeah?
60 and 120.
60 and 120. So 60 degrees is right here. And then you said 120? So we're just going to have one long statement. So we're going to have x such that x equals 60 degrees plus 360k. Or x equals 120 plus 360 degrees times k. And it doesn't matter which order you put these in. Just pick an order. You could put x equals 120 plus 360k first. Or you could put the 60 plus. I usually put the first one, the first angle first. All right. 3 more. One's pretty easy. The other one's a little different. Tangent's going to be a little different. All right. Where is sine of x equal to a positive 1? Brian?
90 degrees only.
90 degrees only.
Pi over 2.
Yeah, let's use pi over 2. So we're just going to say x such that x equals pi over 2 plus 2 pi k. Tangent is the only one that's different. it's going to change your answer slightly just because of where our positive and negatives are. So tangent of x equals 1. Where does the tangent of x equal a positive 1? Rena?
I believe it's 45 degrees and 225 degrees.
And 225 degrees, yeah. So it's at 45 degrees and 225 degrees. What makes this problem different is there's a set interval between these two. To get from 45 to 225, you would add 180. To get from 225 to 45, you would also add 180. That changes our formula just a little bit. We are no longer going to list both of them. Instead, we're going to list x such that x equals our first angle, which is 45 degrees, plus 180 degrees times k. And that takes care of both of those angles. You couldn't do that anywhere else because, for example, if we were up here, 60 and 120 are not 180 away from each other. 60 and 120 are 60 degrees, and then to get back around here is not 60 degrees. It's not a repeat addition. So this only works with tangent values, and it will always work with tangent values as long as both of them exist. If I ask you where is tangent 0 or undefined, that might not work. Actually, it would work. So tangent almost always works using this. All right, the last one is just no solutions. It has no solutions because cosine x, if you look at your unit circle, can never become 2. The biggest number that's on a unit circle is 1, because that's what makes it a unit circle, is a circle of radius 1. So cosine of x equaling 2 would have to be way out here. That would be the point 2, 0. That is not on the unit circle. So it's going to be no solution. It is outside of our unit circle. That doesn't mean that if it's not on my unit circle, like the exact values I have, I'm going to put no solution. So for example, if you look at problems 25, 27, and 29, those you will have to use your calculator. Those you will have to use your calculator to actually get those values. All right, you won't be able to use your unit circle. You'll actually have to put it in your calculator using sine inverse, cosine inverse, and tangent inverse buttons. And they're all in degrees, so you can leave your calculator in degree mode for those. All right, guys, the rest of the time is yours to work.